Now the next part of this lecture is giving you people an exercise at how to construct a truth table. On your screens I have given you some connectives involving two statements P and Q. Now our task is to understand how to compute the truth values in each case. The first of them looks like this. We have P and Q connected via a disjunction, or P and negation Q connected via a disjunction, a conditional, and a conjunction connecting the statements P and Q. Now how do you construct a truth table for this kind of a compound proposition is what we will discuss in the slides that follow. The first thing to note is that it's a compound proposition involving only two statements. So since there are only two statements, only four possible cases will arise. Either both of them are true, or both of them are false, or only one of them is true in two different ways. So this is the very first thing that you'll understand before you draw or you construct a truth table. You'll have to find out what is the maximum number of input sequences that you will consider. It's always a power of 2. So there are only two statements compared here, so you will have 2 to the power of 2, four possible input sequences. And now we are into the problem. The problem says you'll have to find the disjunction of P with the negated version of Q. So let's first negate Q. If Q is negated, all truth values are flipped. That's what you'll end up with. Now you're supposed to do a disjunction with P, disjunction of the negated version of Q with P. So we are focusing on columns 1 and 3. It's easy to lose focus and compare the two wrong columns, so we'll always highlight them. So we're comparing columns 1 and 3, and we are producing them into this, we are submitting them into this connective called as the disjunction. Now recall what a disjunction is. Disjunction is like when you're traveling in a train and you have to submit some proof of identity. You either produce your driving license or your PAN card or both. Only when you don't submit any of them will you be asked to detrain. So if you submit either one of them or both of them, you will still be allowed to travel. This is the example I gave you for the disjunction. Now look at this. Let's compare column 1 with column 3. Now this connective will take up a false value only when both are false. Now do we have anything like that? Yes, the second row corresponds to exactly that. Both P and negated version of Q are false together, and that means the value assumed is a false value. In all other cases, we are supposed to have a true value. That's a very simple understanding of the disjunction. It's false only when both are false, it's true in all other cases. That's not the end of it. We also have a couple of more connectives to do. I'll erase this so that there's no confusion. What's the other connective we have before us? We have a conjunction between P and Q. Now this is going to be interesting. We're not looking at negated version of Q. We're dealing with the actual version of Q. Now we have P and Q, and we're going to connect them using the conjunction as a connective. Now recall what do you mean by a conjunction? It's like gaining access to your email account. Both the username and your password should match with the database. Only when both are right you gain access. Even if one is wrong or if both are wrong, you'll be denied access. So is there any combination where you see both P and Q to be true together? That's when this conjunction will take up a true value, and that happens to be in the third row of your truth table. Look at the third row. We see both P and Q. In fact, we are comparing the first and second columns, and you see that both of them are true only the third row. So the corresponding truth value for the conjunction is true, and it's a false in all other cases. It's a false statement in all other cases. That's straight out of the definition of the conjunction as a connective. Now, are we done? No, we're not done yet. We still have one last connective to perform. What is that connective? It's a conditional statement. It's a conditional statement which says you will have to construct, give me a second, you'll have to construct a connective involving a conditional statement by comparing columns 4 and column 5. We're going to compare column 4 and column 5. You're dealing with them in the form of a conditional. Now, what is this conditional here? We're going to compare columns 4 and 5, and the conditional has its hypothesis in column 4 and its consequence in column 5. Hypothesis is in column 4 and consequence in column 5. You're going to construct a connective involving both. Now, we know this. We have already discussed what a conditional looks like. It takes up a false value in only one case, where the hypothesis is true but the consequence is false. Do we have any such available instance here? Yes, we do have. The first row and the last row have such truth values. You see that the hypothesis is true but the consequence is false, and therefore we have two false values twice, where the truth value assigned is false. And what happens in the other two rows? Look at the second and the third row. We know that the other two rows will always be true, because a conditional returns a false value only when the hypothesis is true but the consequence is false. This is observed twice, and both occasions have been marked with a false value, but the second and third rows correspond to a true value. This is how you construct a truth table. Let's have a look at one more example. In the previous example, we drew the truth table for a compound formula involving two variables. Next up, we'll have one more look at an example where the compound formula involves three variables P, Q and R. Unlike the previous problem, which had only 4 rows of input sequences, we'll have 8 rows this time around. Let's see how they happen. So the three statements are P, Q, R, and you also have the negated version of R as part of the problem. So P, Q, negation R. There is a disjunction between P and negation R, and you have a conditional from Q to negation R. Now, how do we write the input sequences here? Let's do whatever we did for 2 variables and then use a small trick to generate all the 8 rows of the truth table. So these 4 input sequences are what we did for 2 variable formulae. Now, to include the R, let's first write down the value of R is true for all these 4 sequences, and then repeat the 4 rows again, but this time with a false value. So negation R will mean that we will just flip these answers around. Now let's do a disjunction between column 1 and column 4. Column 1 is for the statement P, column 4 is for the negated version of R. True or false will give us true, false again, true, false, true, true, true and true. Now let's go for a conditional between the second row, the second column and the fourth column. False and false will give us false, true and false will give us false. First one will in fact be a true value, because for a conditional we learned that a false value is returned only when the hypothesis is true and the consequence is false. The hypothesis is true and the consequence is false, and this combination is obtained only in the second row and the third row. In all other rows you don't find this combination, and only therefore only the second and third rows will have a false value. The remaining 6 rows will have a true value. The required result wants us to do a disjunction between columns 4 and 5. So column 4 is this and column 5 is this. We will just try and do a disjunction. You know how a disjunction works? A false value is returned only when both rows are false. Both rows are false only in the second row, only in the second row. In all other rows you have true values, and therefore it is T, F, T, 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 T and T. 3, 6, 8. That is how we construct the truth table for a formula involving 3 variables. Let's try another exercise here. This time we are faced up with a conditional. Once again there are 3 variables P, Q and R, which means you will have 2 power 3 rows to the table. And how are these tables populated? We have already discussed that in the previous problem. I'll show it to you once more. You have a P, you have a Q, you have an R. There is no negation R. Now you have a negation Q. You have a conjunction between P and Q. You have a conjunction between negation Q and R. And you have a conditional between columns 5 and 6. You have a conditional between columns 5 and 6. Okay. Now how do you populate columns 1, 2 and 3? Let's write down what works for 2 variables, and we'll just repeat that. That's the smart way to write this down. So both are true in the third row, both are false in the fourth row, only one of them is true in the first 2 rows. What do? We assign all values of R to be true first, and then repeat what happened in the first 4 rows. Look at the first 4 rows. We repeat the same, but this time around all values of R are false. Okay. Now we can complete filling up the remaining 1, 2, 3, 4 columns. How does it work? Look at column 4. Column 4 is a negation operation. You are negating something. What are we negating? You are negating column 2. So the idea is simple. Simply switch all the values. False becomes true, true becomes false, true becomes false, false becomes true, false becomes true, true becomes false. True becomes false, and false becomes true again. So exactly 4 of them are true and 4 of them are false, because you're only flipping them. Okay. So you have completed column 2. Now look at column 4. Column 4 is easy. Column 4 is only a conjunction. You have a connective. That's a conjunction between columns 1 and 2. Now let's recall what a conjunction, or how a conjunction works. A conjunction takes a true value only when both are true. I asked you to relate this with gaining access to your email account. Both your username and the password should be entered correctly for you to have an access to your account. So is there a place where both are true together? Now look at columns 1 and 2 and compare across all 8 rows. Do you have a situation where both P and Q are true together? In fact, yes. Look at column 3, they are true together, and also column 7 when there are 2 together. Therefore, the answers for the rows 3 and 7 must be true. In all other cases, we have a false value. In all other cases, we have a false value. We don't even have to check. By the definition, we can directly write this. And look at column number 6. Column number 6 is once again a conjunction, but this time we are combining columns 3 and 4. Combining columns 3 and 4. Negation Q and R. So do we have a situation where both negation Q and R take up true values simultaneously? If that's the case, then the conjunction will also be true. Only in those instances it will be false in all other instances. Now you can see that that is actually possible. Now look at rows. Let's delete the other markings. Look at row number 1. Both R and negation Q are true together, and also row number 4 when they are true together, but they are not true in any other case. So only rows 1 and 4 return a true value, and it's a false everywhere else. It's a false everywhere else. It's a false everywhere else. That's done. We have populated all columns of the table except one. Now look at the last one. Last one is Paka. It's a straightforward one. It's a conditional. It's a conditional whose hypothesis is column 5 and consequence is column number 6. We have a hypothesis, we have a consequence. And when does a conditional take up a false value? When the hypothesis is true but the consequence is false. Now is there an evidence that there is something like this happening here? Would you like to take a moment to look at the table? I'll give you 30 seconds. Yes, you are right. Look at rows 3 and 7. Look at rows 3 and 7. I'll delete the others. Look at rows 3 and 7. You can easily identify that the hypothesis is true in both cases and the consequence is false in both cases. Therefore, only these two rows return a false value. In all the remaining 6 instances, the answers must be true. And we have completed this truth table also. One more exercise. It's going to be a lot easier. There's only one connective which is going to happen, based on which we'll understand how to determine the order in which you're going to combine them. That's the next thing that's coming up. Okay, this again talks about 3 statements, P, Q and R. You have P, you have Q, you have R, and you're doing a disjunction. Since it is a disjunction everywhere, the way in which you perform the operation is not going to matter, and I've opted for this order. How are we going to complete this table? Let's write down the same thing. We'll write down one set of values for P and Q and then repeat it again for different values of R. Okay, what is R? R is true in all cases. R is false in all the 4 of the remaining cases. This takes care of all 8 possible combinations. Now what does the first one say? The first connective talks about a disjunction between P and Q. So that takes a false value only when both are false, and it happens that both P and Q are false in the 4th and the 8th rows. So in both cases it's false and in all 6 cases that are remaining it's true. And now what is happening? You're combining columns 3 and 4 using a disjunction, and that's the required result. Once again, it's a disjunction, so it's easy to work with. You only look at false value. Are they both false together? Yes, it happens that they're false together only in the last row of your truth table. Only in the last row. And only the last row is going to take up a false value. It's true everywhere else in the remaining 7 rows. That's how you complete this kind of disjunction. So in the past 4 slides, we have had a look at how to complete a truth table. Now there are 3 things to be watchful for. 1, the number of variables that you are involving with, and 2, because that's going to, the point number 1 is going to determine how long your table is going to look like, and point number 2, the various connectives that are part of the given compound statement. Are they conjunctions, disjunctions, or conditionals? You have to look at that. And number 3 is what we'll discuss next, the precedence of the operators. Which operator gets, which operation gets done first. Now when there are brackets like these, like the ones on your screen, it's obvious that you will complete those brackets first and complete whatever is without the brackets. But this is the precedence that we'll watch out for. Any given statement, you always complete the negation first. Negation gets top priority. It's either the tilde or the inverted L symbol that we use for negating a statement. That is always to be completed first. Number 2 is a conjunction, the connective behind the conjunction. Number 3 is the connective behind the disjunction. Number 4 is a conditional when you have one, and number 5 is a biconditional. So when you have, these are the 5 connectives that we have discussed so far, and we've also had a look at the exclusive OR. I'll get to that, but this is how you sequence them according to your order of preference. Negation comes first, conjunction follows next, disjunction, conditional, and biconditional are the ones that follow them. Now we will introduce the next concept, the concept behind a tautology. We'll understand when you call a particular formula as a tautology next, using the same concept of truth tables. Let's perform. Let's do one more exercise. We've done 4 of them so far. Let's just perform one more to understand what constitutes the tautology. We're going to extend these truth tables. That's why I've named them as the continuation of what you have seen so far. This is happening between 2 variables P and Q. You know that. Let's call them, but you see that there are only 2 variables, so only 4 rows will have to be discussed. So P is true, P is false, both are true, both are false. Now what happens when you do a conjunction between them? You must be learning them pretty easily now. Only if both are true, the answer is true. In all other cases, it's false. What about the disjunction? It's false only when both are false. So it's false when both are false, and it's true in all other cases. Now what are we asked to do in the problem? We are asked to think about a conditional statement which has its hypothesis and consequence in the given manner. You have column 3 as a hypothesis statement and column 4 as the consequence statement. Column 3 is hypothesis, column 4 is consequence. Now let's recall how a conditional works. A conditional statement connecting P and Q will assume a false value only when the hypothesis is true but the consequence is false. In all other cases, the condition will take up a true value. Do we have a situation like that here? Do we ever have a place or a row where the hypothesis, as in P conjunction Q, assuming a true value, but the consequence, as in P disjunction Q, taking up a false value? You can see that you never find that happening in the table. You never see that. So you will never have a false value, and hence all 4 rows return a true value for the given compound statement. All 4 values. And this is the first of its kind. Now we have seen so many examples of truth tables so far. Never have we ever come across a compound statement for which all input sequences return a true value. Now this is something special, and that's what we learn under the next heading between a tautology and a contradiction. A tautology is any compound statement which has only true values as its output. So whatever be the input sequence, the output sequence is always true for a tautology. That's what you refer to as a tautology. And the contradiction is the exact opposite. When a compound statement has only false values as its output, you call the statement as a contradiction. None of them add up, all of them end up being false, and that's when you call them as a contradiction. So understanding when a given compound statement is a tautology or a contradiction helps us classify these statements further, and this is of higher importance when we deal with inference theory a little later in this course. So knowledge about tautology and a contradiction is going to help us sometime later. For the time being, we'll just have a look at a couple of examples. Our next exercise is to determine whether the following compound formula is a tautology. Now we already learned that a tautology is a statement which is true always. A statement that is always true is a tautology, and a statement that is always false is a contradiction. We have a compound formula involving 3 different variables and 3 different conditionals. Let's try and find out if this fits into the categories of a tautology or a contradiction. As we have seen before, since the formula involves 3 variables, the input sequence will be across 8 rows. So P, Q, R, the conditional between P and Q, the one between Q and R, the one between P and R. Let's call this as A, let's call this as B, and there is a conjunction between A and B. Let's call this as C, let's call this as D, and there is a conditional from D to C. Let's check how this works out. Let's first write down the input sequences. You must have been familiar with writing the input sequences without any trouble. We have been drawing truth tables for many formulae now. So we'll just write down the sequences for the 2 variables first, and then fill up the rows for the 3rd variable. Now column 1 talks about a formula which is a conditional between column 1 and column 2, and the conditional becomes a false value only when the hypothesis, as in P, is true and the consequence, as in Q, is false. That's observed in row number 1 and row number 5. Row number 2 is false and true, that is true. 3 is true and true, that is true. 4 is false and false, that is true. False and true, true and true, false and false. Column 5 wants us to do a conditional between columns 2 and 3. So false and true is true, true and true is true, true and true is true, false and true is true again, true. Then you have two false values and the last one is a true. Now column 6 wants us to do a conditional between columns 1 and 3. So true and true is true, false and true is true, true and true is true again, false and true is true, true and false is false. For the first time we are having a false value. Column row number 6 is false and false, which is true. Row number 7 is true and false, which is false. And row number 8 is false and false, which is true. Now we are asked to do a conjunction between columns 4 and 5, which is easy because a conjunction returns a true value only when both are true. Both are true only in a handful number of rows, and it is easy for us to do it. First row is a false value, second row is true, third is true, fourth is true, fifth is false, sixth, seventh or false, and the last row is again true. Now we are supposed to do a conditional from column number 7 to column number 6, and there you see that column number 6 represents the consequence and column number 7 represents the hypothesis, and you never have a combination where the hypothesis is true and the consequence is false. Therefore it is true everywhere. False and true is true. You never have a true false combination from 7 to 6, and therefore we end up with a formula that is true for all sequences which are fed as input. Therefore the given formula is a tautology. Tautology. What happens here? We have a compound statement involving only two simple statements P and Q. Let's check it out. This should be easy because there are only two statements, which means you have only 4 possible cases: a P, a Q, a negated P, and a negated Q. So what are the statements here? We'll negate them. We'll negate this also. Now we'll compare them and find 3 conjunctions. All of them are conjunctions. Look at them, all of them are conjunctions. So first between P and Q, next between the negations of P and Q, and then we'll combine columns 4 and 5. Conjunction involving 4 and 5. Okay. So P and Q will return a true value only once, and that is in row number 3. All other answers are false. Now negation P conjunction with negation Q will return a true value only when both are true, and they are never true together. You see, false and a true, true and a false, false and a false. This must be true, I'm sorry. Only in the last case are they true together. The remaining 3 cases, they are false together. Now we are doing a conjunction between columns 5 and 6. Since it is a conjunction, you want both of them to be true to return a true value, but that never happens. Rows 1 and 2 return a false value, and rows 3 and 4, one of them is always false. So all 4 input sequences return a false value, and hence we know that such compound statements are deemed as contradiction. Hence the given compound statement is also what we call as a contradiction. So we have had a look at what a tautology is and what a contradiction is. Now let's go to this next section where we show that 2 statements can be shown to be equivalent. The definition goes on like this. It says 2 compound propositions are said to be equivalent if their truth tables are identical. What do you mean when you say identical? In other words, two propositions are equivalent if and only if the columns giving their truth values agree, they match. They must be 100% match. We actually saw something like this a little while ago. When we discussed a conditional statement and its contrapositive. Look at a conditional statement given here, a conditional statement whose hypothesis is P and consequence is Q. And we also had a look at another conditional statement whose hypothesis was negated Q and consequence is negated P. Now you saw that these two columns were completely identical, false for false, true for true, true for true, and true for true. Whatever sequence we got for the third column and the sixth column, all these answers were identical. It's 100% match. Every input sequence returned the same output, the same truth value. Say they're equivalent only in this case. You say that they are equivalent. Because this is what column 3 corresponded to and this is what column 6 corresponded to. They are found to be exactly equivalent because their columns are identical. They have 100% match, and that is what we see in this slide also. We say that two compound propositions are equivalent if their truth tables are identical. There must be 100% match between the two. Only then this is possible. We'll have a look at one example under this where we are trying to show that they're equivalent. Look at this. This is a compound statement involving two simple statements P, Q and negation P, negation Q, the biconditional involving P and Q, its negation, and also the biconditional involving P and negation Q. Let's find out if these two statements are equivalent. So we'll write down the four possible input sequences. We'll negate whatever we find in Q. And let's go to column 4. Column 4 is a biconditional involving P and Q. And you know that a biconditional is true only when both are true together or both are false together. That happens in rows number 3 and 4. So we have a true value only in rows 3 and 4. It's a false value in others. And now we are asked to negate this. Negation of column number 4. So we'll just flip the answers. Get these. Now let's consider the last biconditional that we have between P and negation Q. That is columns 1 and 3 are to be considered as a biconditional. You know how a biconditional works. It returns a true value when they are identical. So you see that columns 1 and 3 are identical only in the first and the last rows. Therefore you have a true value only in the first and the second rows. In fact, the other two rows are false. Now you see that columns 4 and 5 are completely identical. They are 100% match. All four values of the input sequences have 100% match in columns 5 and 6, and therefore we can conclude that these two compound statements are in fact equivalent. You're just calling them by a different name, but the properties are similar. With this example, we'll wind up today's first lecture on logic. We'll continue tomorrow's lecture with more examples of equivalent statements and the truth table forms of the same. Thank you.